sit down.
Thanks. Okay, well, welcome everyone. My research at Syracuse University was working in solar applications using nanotechnology. So I titled my book, Nanotechnology in Solar Applications, and I kind of labeled it Smart Energy. Okay, so just very briefly, I just want to give you a quick outline of the talk. So I'm going to just introduce smart energy and then talk about solar energy, what's the motivation behind it, why do we want to even study it, what is the science of solar cells, and then look at it briefly about the current marketplace, what is the availability right now of solar cells and the cost, and how does solar really compete with existing energy technologies right now, and then look at some of the challenges that are faced by research in solar cells. And then go on to talk about nanotechnology and how at Syracuse University we were using it to actually try to increase this solar cell efficiency. And then we actually were able to get a grant to try to commercialize our technology. And then to just finish the talk up by talking about the future outlook of solar cells. So when I think of smart energy, the first thing that pops into my head is low carbon emission, and then self-sustaining or renewables, and then energy derived from natural processes. So I think of, wind or solar or the biofuels. And I found this interesting definition. I thought it was a really good definition just from this consulting group. It's a renewable energy consulting group. And they labeled it intelligent integration of an endless supply of renewable energy sources and power consumption to form the future energy ecosystem. And I like how they kind of had on their website these three kind of building blocks. So it wasn't just like, well, you have wind. We need to think about the infrastructure. So we need to build the wind turbines, but then when it's creating energy, we need to be able to store it, for example. So they're saying that smart energy is actually comprised of these three independent building blocks, and that each one is interconnected, and it needs to be pieced together and to form the whole smart energy solution for the future. So why do we want to have smart energy? Well, we want to reduce the carbon emissions. If you just look at, I know this is a couple of years ago, but we look at the US energy consumption for 2010, and 21% is from coal, 25% is natural gas, and 37% is petroleum. 17% is non-fossils, which is nuclear and renewables. And of all of this energy consumption, the carbon dioxide emissions were from these fossil fuels, clearly. I just put in this that we should be careful not to assume all renewables are actually zero carbon, because clearly if we're manufacturing solar panels, in the process of manufacturing them, we are actually creating carbon emissions, so we need to just maybe call the renewables low carbon. It's just something to think about. So why do we want to harness solar energy? Thanks, it's great. Well, the sun, when it hits the radiation hits the Earth and the oceans actually absorb 51% of solar radiation. The rest of it is kind of reflected by the clouds, absorbed into the atmosphere. However, it is a limited source of energy, and the sunlight delivers more energy in 1 hour than the Earth uses in 1 year. So basically, all this combined, there's a huge potential to harness the sun energy. Basically, this is saying that solar radiation on Earth that's absorbed has 7 times the power that the world actually needs, if you look at these figures. So, how do we actually do that right now? Well, we use photovoltaic solar cells. One way of doing it is using photovoltaic solar cells. Photo is light, voltaic is creating electrical potential. So this is a method of harnessing the solar radiation, and then we convert it to electrical power. So you have the sunlight rays coming in here, and then it actually gets absorbed by this semiconductor material, which is sandwiched between two metal contacts, and which creates a electrical current. More specifically, or more scientifically, the actual absorbing layer is made up of something called a semiconductor, which are doped, which just means there's some an element added to an N-type and a different element added to a P-type. And when you put them together, at this kind of junction, when you shine light on it, or photons, it then creates the electrons to move around, which creates an electrical current, and that's how we generate the electricity. And I put this slide up here because as we were doing the commercialization, or trying to do commercialization of our technology, I had no idea that a PV cell was actually made up of all these types of different layers. I knew there was glass there, but I had no idea that there was like at least 7 different layers consisting. This is the absorber layer here, but each layer is critical for the PV cell to work. We learned that even like the EVA, these polymers and adhesives, they need to be certain compositions so they don't melt, or it's very critical to have each layer here. And then the PV panels that you see, they're actually made up of the cells, which are connected together into a module, and then the modules are put together in arrays. And that's the type of solar panels that you see on residential homes, so on the roofs. These ones actually use this semiconductor silicon as a light absorbing material. There's also things called solar farms. I don't know if anybody's heard of them. This is a picture from Nevada desert. And on these solar farms, these panels are actually more capture more light because they're attached to these big motors here, and they can kind of track the sun. So they're able to absorb more light since they're following the sun. And then compared to like if it's just on a roof and your house is only in one position. And so solar costs, this is from 2011, but these are just some of the states that was picked out. New York State, it said that it would cost about $10,000 to install them on your house. And the payback is you buy the panels and it's like an investment for over 20 years or 25 years. So they're saying that in 2011, over 20 years you would save $30,000 or just over. And it looks like Hawaii is a place to live if you want to make some money, because they cost just over $10,000 to install, but yeah, well over $60,000 in savings. So we're in the wrong place, I guess. And then I took this was interesting to learn that the total global energy consumption in 2010, of that total that was used, fossil fuels created that power energy 80.6%, and then the modern renewables was only 8.2%. Of that 8.2%, basically solar PV was 0.06. So we have solar PV 0.06 versus 80% of fossil fuels. And since we're trying to reduce the carbon emission, we really need to up this number and decrease this number. So the reason that they're not widely used so much is so many challenges associated with them. Manufacturing challenges, such as falling prices and tensions in international trade between America and China, for example. Even like global government policies of environmental policies. And then installation challenges. I mean, they're very expensive, and for the roofs, you know, they're rigid, so you only have a limited space. You know, you only have so much roof space. So along with those challenges, we also have material challenges actually within the PV system. So this absorber material, the material that's actually absorbing and keeping the light in there. So like I mentioned before, the most commonly used one is silicon. And these are the ones that are commercially available, and they have a silicon thickness of absorber layer of 200 to 500 microns. Between like 20 and 50% of the solar cell costs actually come from this absorber material. So if we could perhaps like decrease this would be helpful to decrease the price. We have a maximum efficiency of this material of 33%. That's just a theoretical maximum efficiency, but in reality, when you buy them, and they were in those layers, all the layers stacked up and everything, and then you have environmental considerations too, the actual solar panel efficiencies are between like 15 and 16%. So scientists have been working on kind of the top of the solar cells to do surface texturing as one idea to try to increase the light into the absorber layer. So for example, they're talking about, or they have done, making these kind of pyramid shapes, so when the light comes in, it has more chance to bounce around and go into the absorber layer and be trapped there. And this, they actually do this for commercially available solar cells right now. So the ones that you see will have this. You can't see this with the eye. These are electron microscope images. They're only, this is a scale bar of 2 microns. But they have these tiny surfacing textures, so in order to trap the light. And that does work to somewhat degree. However, people are now working on these called thin film solar cells, where the absorber layer is 1,000 times thinner than the commercial bulk solar cells. So we're trying to decrease the cost that way. However, when you are decreasing the absorber layer, you're actually decreasing the efficiency from 15 to like 9% now. And there's many different types of thin film, but I'm just going to talk about the silicon ones. So.
What's the cost, Dave?
Sorry?
It's a cost-performance equation, though, isn't it?
Yeah. I don't know the figures off the top of my head right now, but
Okay.
people are working on these thin film solar cells to put them onto flexible substrates too. So they're lightweight, they're flexible, and technically they'll cheaper because we're reducing the absorber layer. But the thin film solar cells, yes, they have low efficiency compared to the commercially available ones. And they're actually too thin, the absorber layer, to do this kind of surface texturing. So we need to find another way to make them affordable for the end user. So there's a lot of groups, I can't just claim our group did this, there's a lot of groups across America using nanotechnology to actually try to trap the light into thin film solar cells. And I just want to give a quick brief introduction, because everybody seems to hear like nano and it's the big buzzword, and I wonder if like sometimes I don't know that it's very explained very well, and I'm not sure that I'll be able to explain it very well either, but I did find this on the internet and I loved this picture immediately because it kind of describes how I feel about nanotechnology, about both exciting and overwhelming at the same time, because there's so many applications. We have solar here, and oh my gosh, there's like people make devices using nanotechnology. It's, you know, you manipulate on the atomic level, and it's small scale, and anyway, just I really liked this kind of explosion. There's a lot of cells, people using them for biomedical applications. So just to get an idea of the scale, if anybody doesn't know about nanotechnology, is actually studying the science at the nanoscale between 1 and 100 nanometers. So if we look at nanoparticles, which is what I've been working on for the past 5 years, this nanoparticle is 4 nanometers in diameter compared to an ant, which is 4 millimeters. So you think how small ants are, and then you definitely cannot see anything on the nanoscale. We actually have to use special microscopes in order to observe what we make in the lab. And then I just put this slide up not to overwhelm anyone, but just to give an idea of nanoparticles is like a subset of nanotechnology. It's just one tiny thing of nanotechnology, so broad. Like if you think of that as an umbrella, nanoparticles is just one kind of arm. And within that, the inner circle of, like, I would say, these kind of applications of biomedical, healthcare, electronics, and then renewable energy is what I'm going to talk about. But you can see, like, biomedical, they do drug control release and drug delivery, imaging, and molecular tagging, and all this kind of thing. And that's just one tiny area of, like, an explosion. So really, nanotechnology is, whatever you can think of, you can find an application. And I really loved this definition. It was a professor who works with on nanotechnology from Rice University in Houston, Texas. And he was challenged to come up with a definition of nanotechnology in 7 words. And he came up with making small stuff do big things, which is 6 words. And then he thought to himself, but that's not really the end, because if you just do that, then you're publishing your results and burying it into the scientific literature. We need to kind of sell them and make them useful for real-life applications. So I really liked that definition. Oops. Okay, so nanoparticles, this is what I was working on in Syracuse. And we were making something called plasmonic nanoparticles. Plasmonic nanoparticles are actually made out of gold or silver. And when they're under 100 nanometers in diameter, they have this size effect which interacts with light. Sorry, when light shines upon them, they absorb light, and these electrons oscillate back and forth. And this is called a surface plasmon resonance, when the electrons oscillate back and forth when they interact with light. And just some real life applications, Notre Dame in Paris, these stained glass windows were made many years ago, way before we even knew about nanoparticles. However, they must have contained small flecks of gold, because when you see any kind of red in stained glass windows, it's to do with really small flecks of gold. So that's kind of the beginning of nanoparticles. When gold nanoparticles are in solution, they're red, and when silver ones are in solution, they're kind of yellow. So, which is this slide here. So we can actually tune the optical properties of metal nanoparticles, these gold and silver ones. These are silver nanoparticle solutions, different colors, and these are gold nanoparticle solutions. So we can change the color by the material, we can change the color by the size. This is red. These are gold nanoparticles of only 5 nanometers in diameter, and as we increase the particle size this way, this one here is a blue solution of a nanoparticle with 150 nanometers in diameter. And we can actually make different shapes as well. We don't have to just make spheres. We can make rods, nanorods, and these absorb in 2 different regions of the visible spectrum. We can actually force aggregation, and that will shift the absorption wavelength. So we can kind of tune in the visible spectrum wherever we want to absorb. Now, I mentioned that some people in the literature also were working on this, and they kind of were doing modeling of this. They were showing us that we could put these nanoparticles onto the surface of a absorber layer for the solar cell, or we could embed them in there, and that there were 2 different mechanisms, light scattering or concentrating the light, and they would actually increase the efficiency of thin film solar cells. then they work. It'll do both. It'll scatter the light, so it traps the light. Sorry, it absorbs the light, and then it will trap the light because it can't really get back out with the particles on there. So it basically increases the optical path of the light within the silicon absorber layer. So the groups that were working on these, some of them names are here, and these are the publications, but they were basically taking silicon and then depositing metal film, and then using these techniques which are high energy cost and high temperature, high vacuum, like thermal evaporation, in order to kind of basically create these nanoparticles. So what you're seeing right now is nanoparticles on silicon, and these images were taken by a scanning electron microscope. And you can see that these, for example, this one, they're very like ordered, so you have an ordered array, and they're very uniform in size. And this was commonly thought that this was the pattern we needed in order to increase the efficiency of the solar cells. But we decided that we would try different routes. I done a lot of like chemical synthesis, so we tried to develop a cost-effective, room temperature, scalable route to make these nanostructured interfaces. So rather than using these very like expensive techniques, which kind of is, we're trying to lower the costs in all ways. So if we can come up with a room temperature, cost-effective way, scalable, and then could we replicate these things, and could we test our nanoparticle interfaces in a photovoltaic system, and basically can we increase the efficiency of the electrical output. So these were the two things we were looking at, amongst others. And I basically put this slide up because I wanted to show that this is spectral radiance, which is sunlight intensity over certain wavelengths here. And this is the solar radiation spectrum. So here we have the yellow is the sunlight at the top of the atmosphere, and the red here is the sunlight radiation at sea level. So you can see really in the visible spectrum from like 400 to 800, this is where the maximum of the solar radiation occurs. And there's a discrepancy, obviously, between the sunlight at the top of the atmosphere and the radiation, and that's due to the other diagram I showed you that only 50% gets absorbed. So we were thinking about that, and we actually made up these, we created these multi-component plasmonic nanoparticle solutions. So we could basically make the whole kind of rainbow spectrum, which is what we want to really focus in on. We're trying to trap as much of this sunlight as possible. So we thought if we could make these plasmonic nanoparticles and get broadband absorption, which we did right here, so from 400 to say 800, we have all this absorption here. If we could then put this onto our solar cells, we could trap that light, and it would absorb more and hopefully increase the efficiency. So we did some tests in the lab first. We just took we didn't want to use a solar cell straight off. We just took some silicon wafers, and we put our silver nanoparticles on, spin coated them at room temperature to see if they would stick onto the surface. And we just looked at kind of surface coverage versus the amount of nanoparticles, and we could see that if we doubled the amount of nanoparticles, we could double the amount of surface coverage. And then we got to a kind of maximum surface coverage here of 68 using this 5 weight % of nanoparticles. But we took these images and we just kind of wanted to see if they would stick there and stay. And as you can see, these images, they're kind of random compared to the other ones, which were very kind of ordered. So we didn't know if that was going to make a difference or not. We just continued with our tests at the time. We wanted to see if it would go onto glass too, so we did the same experiments and put them onto glass. And then we checked the absorbance, so without any nanoparticles, you'd have a flat line here. So with the nanoparticles on, we're getting an increase of absorbance, and this is what we want in the visible range, because we want to trap that light and absorb it.
And that's all at room temperature?
Yes. And then we also made some flexible interfaces, so we were able to put our particles into these polymers and create these flexible films, because we were thinking in our minds about the picture I showed you of the thin film solar cells on flexible surfaces. So we were thinking to put our films over the top of flexible thin film cells too. So having had these initial results, we then did kind of like mimic of a solar cell. This is called a silicon on insulator device. Basically, it's a photodetector. We had two metal contacts here, and we have this silicon device layer here. This is our absorber layer, and we put the nanoparticles on top and then shone light on it, and across the wavelengths we were able to detect photocurrent. And then, so basically the experiment we did, we took a range of different silver nanoparticles concentrations, and we wanted to see if they would increase photo efficiency. So we started off with 0.01 weight percent, and we saw that it increased, and then as we went up to 0.05 and then to 0.1, we saw that we were increasing the photocurrent efficiency of this particular silicon on insulator device up to 150% weight. Sorry, 150%. And then as we increased the nanoparticle solutions, we actually got a decrease here. And we weren't too sure actually why we got the decrease. We thought there would be kind of like an optimal concentration and an optimal surface coverage. I guess maybe naively we were thinking the more you put on the better, because we were thinking we want as much light trapped as possible and absorbed as possible. So we were thinking if we put more on, but it actually turns out if you have this 10 weight percent, you get far too higher coverage, and they start interacting negatively. So the optimal one was the 0.1 weight percent here. And sorry, these are nanoparticles on the silicon on insulator device. And we looked in briefly to try and find out why we were getting the lower efficiencies with the higher surface coverage. And we saw in the literature they had something, these capillary forces cause the particles to aggregate in clusters and chains, and we saw that people were purposely making chains of nanoparticles, and that these actually, when they go in a chain, it actually causes this peak to shift to the red. So, and we saw that they were making clusters, and that also causes a red shift in the visible spectrum. So we started to look more detailed at our surface morphology of the SEM pictures here. So these are nanoparticles on silicon, and we started to color in our clusters and our strings, and we could see that we had quite a lot here. And then so we just did an experiment to check these silver nanoparticle solution weight against the surface coverage, and we counted up each ones to see the number of clusters, which is the red line here, and the number of strings, which is the blue line. And we can see that as we increase the silver nanoparticles, the strings and the clusters increased, and obviously the black line is the surface coverage, which naturally would increase. So basically, we found that we could make a cheap, fast, and effective way of creating these nanoparticle interfaces and at room temperature. We believe our method is scalable. I mean, this is lab research in a university, so it is very small scale, and we didn't have the means to try to scale it, but we spoke to people in industry and they use spin coating, so we were using spin coating, so we figured that it would be scalable. And then we saw that we got up to 150% current increase using these silver nanoparticles at 40 nanometers. And these are just like kind of preliminary results really. There's so much, this could explode into so many more experiments. There's many possibilities for tailoring the particle parameters such as shape. Like you can make all different types of shape. I just gave you kind of a few examples. You can make cubes and stars and everything. Or tuning the size and even the materials. Gold is kind of expensive, so that's where we're really looking at silver. But I think if you mix some of the materials together, you could try and find the same properties, but that's for another person to do. So. And while we were doing this, we actually applied for a grant from the National Science Foundation to do, they have this new kind of course, is to try to commercialize or see if there's commercial potential for technology. So we went down to Georgia Tech two summers ago, and then I just went back to thinking of that quote I found, making small stuff do big things, and then we were trying to tell them. So when we did this, it basically was kind of like they made the grant requirements were that we had to talk to a large number of customers, and we had to come up with a name. So we came up with a name of NanoPaint, and we were going to try to see the commercial potential for solar applications. So I personally talked to a lot of people at DuPont, First Solar, GE, Sharp, BASF, Corning. There was a lot of people we talked to. Boeing, they were really interesting to talk to, and BAE Systems, spoke to somebody earlier, and ETM Solar, I think they are in the
Endicott.
Yeah. So we spoke to installers, we spoke to manufacturers, and basically we got as much information as we could. And some of the key learnings, it just was very interesting to talk to people. Somebody at DuPont told us that photovoltaic cells lose 0.2% efficiency for every 1 degree temperature rise. So if you have a 10 degree increase, you get a 2% efficiency loss. And when they're already only 15%, a 2% efficiency loss is huge. So he was saying, not only do you need to try to increase the light being absorbed, you actually need to maybe make a heat-reducing coating for the cells, because this would have been of immediate value yesterday. I mean, clearly there are solar cells that work, so there are already kind of heat-reducing. There just could be so many more things that can be done with them. There can be so many more tweaks to make them more efficient. And this was a quote that I kind of already mentioned, that it drops to approximately 15 due to heat damage was another. So then over 2 months I talked to as many people in this PV ecosystem, I call it, as possible to find out how valuable our technology actually was to them. Somebody at GE told us really the bottleneck in the industry is actually the silicon, and that's because it's something called a direct band gap. Doesn't really absorb light that well. It's supposedly cheap and abundant material, but so there's many people working on other kind of materials, not just silicon. The PV, we spoke to PV manufacturers, we spoke to glass manufacturers because they actually make glass for the PV manufacturers. And then, like I said, the installers we spoke to. There's solar consortiums, we spoke to people in there, and there's a lot of academics working in this area. And then what a key learning for me was this polymer that they use to kind of stick those layers together. Because our nanoparticles are solution-based, they're water-based, and so is this EVA polymer. Sorry, it's not written there, but it's called something called an EVA polymer, and that's water-based. So we were thinking, could we just put our nanoparticles into this polymer system, since we'd already made polymers, flexible ones anyway. So we spent a lot of time trying to find out where would our kind of nanopin go in the PV cell, and which customer segment was going to put it there. We kind of thought that we would maybe do a direct sell to glue manufacturers or even the PV manufacturers, and they would then put everything together and then sell it to the PV installers and get to the end user. But during this time, towards the end, we were actually speaking to Yingli Solar and Sharp, and they told us this key bit of information about the photovoltaic industry is very nervous about unproven tech supported by small unproven companies. And if we started up our own company, we would be a small unproven company, a spin-out company from Syracuse. And they said that reliability, credibility is key to the photovoltaic manufacturers, which is obvious. And then they told us about this company, from a spin-out company from a Californian university, I can't remember which one. It was called Innovolite. They had a great technology. It was a light trapping technology. It was actually using silicon nanoparticles in solution, and they were a startup company, and they lost $8 million trying to sell to the directly to the photovoltaic manufacturers. So they went out of business, and DuPont bought them, put their seal of approval, and now DuPont sells that technology. So we learned we were not going to lose $8 million. So we decided that we would not start up a company, and that we would actually go more down the licensing route. And we were, at the time, talking to DuPont. The grant ran out I was working on, so my boss is still trying to talk to DuPont about doing this licensing. But so basically, long story short, the photovoltaic industry is pretty brutal, and I think their technology is more within, and they try to hide it too a lot, because it's just a very competitive industry right now. So, but just to talk about the future, I think, with the energy demand, we really do need like clean energy sources. We need to lower the carbon emissions. So right now there's just an enormous gap between the huge potential of solar energy, and the bottom line is we need to make them affordable for kind of everybody to use. So really, I personally think, and a lot of people in the scientific literature are talking about using nanotechnology and really interdisciplinary research. I feel like I always think the more heads together, the better the results. So if people can actually work together on this, I think, this will take off eventually. It's just a cost factor. And just to kind of acknowledge the people I worked with, my boss, Professor Suresh Kumar, and then Tao Kong. He was a PhD student at the time. He helped a lot with this work, and Peter was a master's student at the time, and he helped a lot doing the spin coating. So definitely want to acknowledge NSF for the funding. And this is Syracuse on a sunny day, which is not happening often. And this was our department right here. So, and thank you all for listening. And if you have any questions, I'd be happy to answer them. So, and if not, that's okay too.
A lot to absorb.
Yeah, I know.
Photovoltaic joke.
That went right over my head.
Who got a question here?
Yeah.
So basically what they're already doing is doing these little nano textures, let's call them that.
Mm-hmm.
So what you're trying to do is kind of apply this nanopaint stuff, sort of like put it in or on, and that would help too, or?
Yeah, we thought about just putting it on, but we think that we had to put it inside the cell. It had to be as
So it
close.
doesn't evaporate and stuff.
Well, that's one way. Yeah, you definitely don't want it to evaporate. You don't want it to have sun damage. So the right now at the top of solar cells, they actually have something called an anti-reflective coating. So the most sunlight can come in, but it doesn't allow for sun damage. So if we put ours on top of that, we would get sun damage on our. So you need to have the nanoparticles as close to the absorber layer as possible, because it concentrates the light, and the silicon actually helps concentrate the light too with the nanoparticles there. So you really need it as close to the absorber layer, and the absorber layers, I don't know if you remember my slide, but there was like all those different layers. So the absorber layer is kind of in the middle. So we needed really to get the kind of nano paint right next to that. So.
A question.
Mm-hmm.
Solar panels, the standard solar panels basically seem to be angle dependent. So like if this is the panel and the sun is exactly 90 degrees, you get the most efficiency, and then as the day goes on, you get less and less efficiency.
Mm-hmm.
Did you see any increase in efficiency using nanoparticles on the attack angle, if you will?
That would be an interesting thing to study. We didn't study that. We
Okay.
just kept it at one angle.
Okay.
We were shining light like this.
Right.
But that would be interesting, because they scatter light. So
Mhm.
I wonder if that would make a difference or not, because they're actually absorbing and then scattering the light
Right.
into it. But
Like we've got solar panels here, like I have solar panels
I
in
know
my
you
home.
do, yeah.
And you see it, when you look at the response over the day, as the sun's coming up, there's very little, energy being collected, but then as they get to noon, it peaks, if it was a completely clear day for the entire day, and then it goes back down again. So now, some of those solar panels that are motorized,
Mhm.
and they will sit there and try to follow the sun wherever it is to try to maximize how much light, the efficiency. And I'm thinking that might be an interesting experiment to,
Yeah.
as you change the angle of attack,
Mhm.
does even, almost like doing like a surface coating of it, just to sort of keep trying to, refracting it down, into the.
Right,
into the
yeah.
sun.
Yeah, no, that definitely would be interesting to
I'm
see.
sorry, there was another question?
Yeah.
If like solar panels are coated with anti-reflective coating, why are they still sort of glossy-ish?
That's a good question. I don't
Sorry,
know.
what was the question? I didn't get that.
She was asking about if solar panels still, if they have an anti-reflective coating, why do they still look like shiny, basically?
Oh.
So.
Did they ever use, have you guys tried using anything other than silicone in the solar panels?
We personally didn't, but there are other groups working not using silicon. They're using a whole different type of semiconductors. There's many different types you can use.
Actually, I think Binghamton University has a center called CASP, the Center for Autonomous
Yeah,
uh,
autonomous.
Solar.
Yeah, solar power.
Yeah,
or
right.
Yeah.
And they're looking for, even as plentiful as silicon is, if you will,
Right.
is, looking for less expensive materials.
Mhm.
They aren't quite as efficient,
Yeah.
but if you can reduce the price point, and you got plenty of space to
Right. Well, I heard something about graphene, and I didn't know.
Okay. I haven't heard about graphene. I know they're working using stuff like calcium telluride
Yeah.
and something called SIGs, which is, honestly, off the top of my head, I can't remember all the different elements, but you're right, I've been to that group, the research group, and saw there.
Yeah.
Would your technology translate to the other things, or is it only derivative to silicone based?
We think it would translate to the other types too.
Yeah.
We haven't tried that, and that would be, the problem with university funding is always
Yeah.
short time,
Right,
but we
right.
always have like more experiments to do after, but that would have been a good set of experiments to do too.
Okay.
Yeah.
So as all the looking around that you did to all the private industry, was there any government industries basically doing any study or research on any of this?
We didn't speak to any government. I'm certain there are. They're also keep their cards close to their chest, so I don't know that they would give so much information away, but we didn't speak to any government ones, but yeah.
It also occurred to me that you have some sort of specialty solar panels, like one specifically that are flown in space, that you may be not making a whole lot of them. But
Right.
if you whatever you can do to reduce the size and increase the efficiency,
Right.
that might be a market. It may be small, albeit small, but at least
Yeah.
it's a market where that, if you only got so much space, if I can get, very often the size of the spacecraft depends on how large of a solar panel you can get
Sure,
away with.
yeah.
Conversely, if you can drive the cost down, find materials that you can drive the cost down, then the efficiency may not be as important because you can put these stuff anywhere.
Yeah.
You can just kind of coat the surface of coat the top of a car.
Right. Yeah.
I know you were experimenting for our room temperature thing,
Mhm.
but did you try checking if it was affected at all by temperature? Because outside it gets really hot or really cold sometimes.
That's a good question. That is. We did after we spin coat them at room temperature, we did put them in ovens at different temperatures to see if high temperature would affect them or not, and they seem to not. We test them afterwards, and they seem to not be affected by that. So, but that's a good thing to think about. Yeah.
Because if it's December and the solar panel gets snowed upon, then we can't have nanopaint getting room.
That's because the nanopaint has to be sandwiched in between all the different layers.
It's too cold.
Yeah. No, we thought about that too. These are good questions. Yeah.
So a standard solar cell has a very limited range of absorbance as compared to one that is coated by nanoparticles. And is it much more narrower as compared to one that is coated by nanoparticles, a standard solar cell? The range of absorbance of wavelengths?
I think the silicon one absorbs within a certain range. I heard that was, I don't know the range it is, but that's what we were trying to increase the range
Right.
by putting our nanoparticles on top of it, increase the spectrum.
Right. No, I just think it's really cool because plants have been doing it for 3-4 billion years.
Right.
But they have a very narrow range of absorbance.
Mm-hmm.
And your research, you're just increasing that range of absorbance
Mm-hmm.
to a full broad range between 400 to 800
Mm-hmm.
between that wavelength. So I just think it's really cool.
Thanks. Yeah. I thought it was cool too.
I'm sure Jen will be willing to stay and answer any additional questions. Roy, what's the sky look like?
Yeah, what we have is, we got some clouds, but I'm going to dim the lights a little bit. So we have Saturn in the 6-inch telescope and also the 20-inch, and we got Mars in the 14-inch. All right, so if you want to hang out and talk to Jen for a while, that's fine. The store is also going to be open, and we have some tea out here for just 75 cents if you want some of that. And don't forget the Apollo 16 moon rock in the lobby. You want to check that out?
This summer we've got a lunar sample that was brought back by Apollo 16, and it's over in our sort of astronaut Hall of Fame, along with our space shuttle computer.
Okay. So,
And the reason we got the red lights on is just to try to keep get your eyes to.
the blue didn't help, but okay. So we're right this way. We'll kind of divide you up.
Thanks again, Jen.
Oh, yeah, no, thank you.